This is Jack Jackson. This video we'll be talking about doing confidence intervals and also hypothesis tests for variances and standard deviations where we have two independent samples from normally distributed individuals. So this uses what we're calling an F distribution, which we reviewed a little bit in our last video, and this will give us what we call an F test and an F interval. They test for differences in variances or standard deviations. It's not robust with respect to the normality requirement, so both samples must come from normal distributions. Not just the distribution of sample means, but the individuals must be normal. And the TI-84 and TI-Inspire and FPDF and FCDF functions are built in, so we can use those. The TI-84 does not have an inverse F, but we have a program for that. The TI-Inspire has a built-in inverse F function. Both have a two-sample F test, but they do not have, or at least the TI-84 doesn't have, a built-in F interval, but we're going to make a program for that. So the F interval works like this. It's just a lot like the chi-square interval for one sample standard deviation. It's very similar here, but it's for a ratio of two standard deviations from two samples. So over here we have the ratio S1 over S2 from our samples, and we divide by an F value, and also over here. So this is our F upper. That's an F value from a distribution with the degrees of freedom figured out by one less than each of the two sample sizes. And that's going to be the F value where there's an area under the PDF or a probability to the right of alpha over 2. So 1 minus alpha over 2 will be to the left. And then this one's just the other way around. It'll have F to the left. The probability to the left will be alpha over 2. So this is actually an inverse F of alpha over 2, which is our F lower here. And our F upper here is inverse F of 1 minus alpha over 2. The inverse F's we can get from a built-in function if you have a TI-Inspire, or from my program if you have that for the TI-84. And if you want to do change this into an interval for sigma 1, it would be some number times sigma 2 and the same number times sigma 2 here. So it's really an interval that's best, I mean, it's sort of best to do this one at the top. So it's an interval for the ratio of the two. So let's put this into work for an example. One year at Arizona State University, a new teaching method was attempted. The experimental group was taught with the new method, and 20 students from the group took a common final exam. The sample standard deviation of this group was 5.286 on the assessment. A control group was taught using the old method and had 41 students taking the final exam. The standard deviation of this sample was 7.813. Assume that these are random samples from normally distributed populations, independent samples. Perform a test of hypothesis to test for a smaller standard deviation in the experimental group. Use a 5% significance level, and also construct a 95% confidence interval for the ratio of the standard deviations. Well, the null hypothesis is that sigma 1 equals sigma 2, or sigma 1 over sigma 2 is 1. The alternate hypothesis, or alternative hypothesis, is that sigma 1 is less than sigma 2, which is to say that sigma 1 divided by sigma 2 is less than 1. It could be phrased either way. So our F statistic is S1 over S2. The sample sizes were 20 and 41, so the degrees of freedom are one less than that, 19 and 40, in that order. Okay, so let's see, I got some bunch of screenshots here. So what do? We found the S1 over S2. First of all, that's our let's see, where is that? Standard deviations, not variances, are given. So 5.286 was for for the first one, 7.813 for the second one. We do that ratio. Then we square those because these are S square over S squares for our test statistic, which is F. So I stored that as F, so that's my F value, 0.4577397931. Then I took that and then did an FCDF. We're doing a left-tailed test. Remember, we're testing for less than. So once again, that sigma 1 is less than sigma 2, or less than 1 here for the ratio. So that's a left-tailed test. So we want the probability to the left of this F test statistic. So that's 0 up to that F with 19 degrees of freedom from the numerator and 40 for the denominator. That's an FCDF function, which returns our p-value of 0.0348. I've illustrated that here by graphing an FPDF and then using calc, which is second trace, and number 7, our area calculator, and telling it from go to 0 up to what we have stored as F, and it shades it. So there's the p-value shaded. I could have also done a built-in shade F to get that shaded if I wanted to. But in any event, there's our p-value, and that's what we really need to make our decision on the test. With a p-value of 0.035, that has to compare to an alpha of 0.05. It's less than alpha. So when the p is less than alpha, we see that there is enough evidence to conclude that we can reject the null hypothesis. So in this case, that means that the experimental group had a smaller standard deviation on the final exam than the control group. Luckily, this is all built in the calculator, so you can use a 2-sample F test on the TI-84. They have a similar thing on the Inspire. We go down, we can choose data if we have the 2 data lists in, say list 1 and list 2. In this case, we have the summary statistics, so we just go to stats. It's going to ask us for this S1 and the N1, the S2 and the N2. Just type those in from the problem. We want a left-tailed test, so we choose the one in the middle. You can do calculate or draw. If you draw, it's going to draw something similar to this right here, where it illustrates the p-value. And then we can, but most time we just need a number, so we're going to choose calculate instead. It gives us this screen here. The alternative hypothesis is that sigma 1 is less than sigma 2. The F test statistic is 0.4577 something, same as we computed up here. The p-value is 0.0348, same as we computed here. And the sample standard deviations and the sample sizes here are repeated for us, which is what we gave here. Of course, if we'd done data, we wouldn't have known what these were ahead of time, but it's going to return those. Now, particularly when you have enough evidence to reject the null hypothesis, it's good to give a confidence interval as well. So let's do that. We need to do an inverse F for this. So to get this F alpha over 2, we need to have alpha, well, to get the F1 minus alpha over 2, that's 1 minus alpha over 2 to the right of F, or alpha over 2 to the left. So alpha over 2, it turns out to be 0.025. So we graph that horizontal line. And we're going to calculate the intersection here, there to be 0.4286. That's our F lower, so I'm going to store that as L somewhere. Here it is. Okay. And, well, actually I'm not going to store it as lower. I'm just going to take that as my X value that I just did. Now I'm going to go ahead and compute the upper limit from that. And it is S1 divided by parentheses S2 times the square root of that X value that we just found. And I'm going to store that as the upper because that's this upper limit right here. So that's 1.0334. Similarly, I can graph y equals 0.975, which is excuse me, 1 minus alpha over 2, which is what's to the left of the upper F value. I'm going to find where these cross. Do the same calculation with that X value. And so that's going to produce my lower one. And so that's the 0.04684, and that's going to be our confidence interval for the quotient here of the 2 standard deviations. Now, you could have also found these these values here, the 0.4286 and the 2.086, you could have found those by doing the inverse F if you have a TI Inspire, or you could have found them with my inverse F program. However, I'm going to program this whole thing in. So here's the final program for the semester for the TI-84. It goes across this way, this screen, and read it like you're reading a book. Go across this line, next enter this, then this data, then the next line, and then the next line here. Enter all that in as a program. This will produce both a confidence interval and a hypothesis test. So let's put this into work. As always, if you can make it to the UAFS, University of Arkansas Fort Smith campus, I will plug your calculator up to mine and I can give you this directly. So this program is called F interval. This is for doing an F interval. There's a built-in hypothesis test. So I think take that back. I think I just said that produced a hypothesis test and a confidence interval. There's no need for a hypothesis test because you already have an F test built in, but not an F interval. So this will take care of the interval part. It produces a confidence interval for the standard deviation, actually a ratio of two standard deviations for two sample. We can choose to go from data or stats. If we have our data in, say, list 1, list 2, we could choose that. If we choose stats in this case, we enter in the sample sizes, 20 and 41, the standard deviations here and here for the sample standard deviations, and we find a confidence interval for sigma 1 over sigma 2. There's our lower and our upper limits of our confidence interval, and that's exactly the same numbers, see, that we produced on the previous slide when we worked it out by sort of by hand there, not completely by hand, but so now that program allows you to do a confidence interval. So now we have calculator shortcuts for basically every single thing in this unit. We can do either the built-in apps in the TI-84 or the programs that I've written. You have all the grunt works done by the calculator. So we're going to summarize this a little bit in our next video.